can all hear me? So let me start by welcoming you all to the Earth Observation Australia's webinar. So I begin by acknowledging the beautiful country upon which we live in, and just some housekeeping to let you know that the proceedings will be recorded. So I hope all of you are in agreement for recording to take place. And we have a reference to Earth Observations Australia Code of Conduct regarding that we need to abide with. So today's topic is going to look at assessing Australia's stored water from space. We all know that Australia is sort of disadvantaged in terms of groundwater and surface water. We don't have as plenty as other areas. So the little that we have, we need to preciously treasure it, and monitoring it from space is one of the ways that we tend to take care of the little that we have. So today we have three presenters who will be talking about methods of monitoring the water from space. And the main aim is to understand how Earth observation products and techniques can be used to support monitoring of Australia's water. We'll also look at the update of AquaWatch in Australia, and then we need to have some awareness on the state of art of Australia's stored water, the challenges and the future directions of the stored water. And the fourth aim will be to present the use of machine learning groundwater models to interpret hydrogeological features in different areas. So the outcome we expect in today's webinar is to familiarize with Earth observation and other tools that can be used to support monitoring of stored water, to understand the AquaWatch and its status, and showcase the gap between hydrogeology, remote sensing, and computational science. We thank our coordinator, Larissa, who has really put together all the things that we're going to do today. And to start us off, I will introduce the first presenter of today, who is Dr. Mehdi Khaki. Mehdi Khaki is a lecturer at Newcastle University and has worked in the areas of assimilating hydroclimate and model data. So his topic today will be looking at possibilities of assimilating satellite observation data and model data and how that enhances the monitoring of water. His bio is in the link provided. You can read his bio in the link provided. So without taking much time, welcome, Mehdi.
Thanks, Joseph. Thanks for the introduction, and hello, everyone. And yeah, I guess I'm ready to start my presentation. If I just share my screen. And I leave the chat open. All right. So can you all see my slides? All right, thanks. Thanks, everyone. So welcome to this webinar. I'm going to talk a little about my research during and after my PhD, and with the focus on my works on assimilation. So try to keep my presentation within the 10-11 minutes, hopefully. So just a bit about myself. My name is Mehdi Khaki. I'm a lecturer at the University of Newcastle. I joined this uni after graduation, after my PhD graduation from Curtin University in 2018. My background is on geodesy and satellite remote sensing, and that's and from my PhD and during the PhD, I started working on this topic on integration satellite remote sensing with land surface models to improve their simulations and later to improve their predictions. So, and that's what I've been working on ever since. So just a little background about the problem I've been working on. So measuring and basically quantifying a water storage component, including, for example, groundwater, soil moisture, surface water are important for our society, for our country, especially in Australia, which is a dry continent. It's very important that we can accurately monitor the changes in water storage within the land. And this is a challenging task if you just want to rely on in situ and ground measurements. So hydrological and land surface models are very useful tools to help us with this type of monitoring. Nevertheless, they have their own limitations, which can be caused by limited input data sources, uncertainty or inaccuracy of the input data, oversimplification of physical phenomena within the modeling mathematics, and so on. So to deal with all these, one of the ways that we can actually address these issues is through data assimilation and using particularly satellite remote sensing, which provide us with global coverage, high spatial temporal resolution, especially these days with the developments in the satellite platforms that we have. So this is basically the rationale behind my study. I'm trying to use various satellite products to improve the land surface models and to improve their capability of for accurate monitoring. So the main idea behind data assimilation is highlighted in this slide is to minimize the discrepancy between the model and observation data. I'm not going to go into too much detail about the method. It's not enough time to do that, but just give you some idea what's data assimilation. Imagine that you have some sort of simulations from the model. Then you have some measurements like X in this graph, and data assimilation help us to decrease this offset between the model and the reality or direct observation through some mathematics, through some, for example, filtering like Kalman particle filtering and some numerical methods. Based on the accuracy of the observation and our model. So based on the uncertainty in both, we try to minimize this discrepancy and we get better estimates like this red graph. So that's what we do. So we try to improve our simulations based on the new observation, whenever the observation is available in terms of location, time, etc. Various satellite products can be used for this. I particularly use mostly GRACE satellite gravimetry data throughout my study. GRACE is GRACE and GRACE follow-on. These are gravity missions that provide information about mass change between the Earth, ocean, atmosphere. Specifically over the land, this information can be very useful in quantifying total water storage changes, which can be, again, used to improve the model. So a majority of my studies I've been using GRACE products for improving the water storage components. And one of the advantages of using the model is that you can actually disintegrate the total water storage data that we get from GRACE into various components like soil moisture, groundwater. So we can improve those components while we get this kind of separation in the total water storage data. I'll also been using other data products like soil moisture. In some of the studies, I showed that combining soil moisture and GRACE total water storage data can result in a better estimates ultimately. Especially by concerning the soil component using the soil moisture observation from satellites. To this end, I use, for example, AMSRE satellite, SMAP more recently, and SMOS in different basins. In my study, covered basically different areas, as I'll show you in the application, from global to local and some basin scale. I also use leaf area index from satellites and reanalyzes to improve the models. And in one of our last works, I also use satellite radar altimetry to drive surface water storage for the assimilation. So all these can help us. It depends on the application, depends on the area that you're focusing on. One or more of these satellite measurements can be very useful to improve the estimates. But having the multiple observation at the same time can be a challenging task when you do the assimilation. So this is in terms of method. We have model. Basically, I tried to make a very simple chart. We have model. We have data such as GRACE, and through the assimilation, we try to constrain the model simulations based on observation and based on the uncertainty, and to get a better output in the end. If you do this properly, you can also have some good prediction because you have better initial stage for the prediction for the forecast period. And if you do the calibration as well as the data assimilation, then you can have a even potentially better estimate as well. This is another thing that I'm working on, and one of the techniques that we use, which is based on ensemble-Kalman filter, is basically has been developed to allow us to assimilate new observation at the same time, calibrate the model parameters, some of the model parameters, which can result in more stable, more reliable forecasts. Some applications, some of the studies that I've done previously. So for example, I showed in this specific study that models can be useful, especially with the application of data assimilation to study groundwater and total water storage in areas that we don't have, for example, good data coverage, good ground data, like in this case, Iran. I showed, for example, if you look at this graph on the left-hand side, the black graph shows the model outputs without any assimilation over different parts of the country. Red shows after the GRACE data assimilation, and you can see we are able to better see the negative trend in total water storage, and in this on the right hand side in the groundwater storage. So the negative trends in the groundwater and total water storage changes have been identified basically more accurately after the GRACE data assimilation. Another study was, for example, that what we've done over Bangladesh. So the challenge was in that case was abundance of the surface water. So we had to use some satellite altimeter data to get some understanding about the surface storage. We then remove that surface storage from GRACE data product and then use the remaining to improve the model corresponding component, mainly groundwater. So this is why I said you need to be careful about the case study, about the conditions, and what you want to use as data as observations. Another study here, we used, again, GRACE and soil moisture observation, satellite soil moisture observation to analyze groundwater changes and groundwater trends in South America. And we could identify trends in different basins and using the data assimilation. And further, we use that to make focus on groundwater and soil moisture, especially on temporal variations. And in all those studies, we evaluate the results using independent measurements, like, for example, in situ or bore data for groundwater, to make sure that the assimilation actually works and improves it. And in most of the cases, this was happening. So using specifically GRACE and satellite soil moisture help us to more accurately represent groundwater changes and soil moisture variations within the case studies. And this was one of our last works in the over the Middle Eastern area. Again, we don't have much data in this area, in this part of the world, and relying only on model, we couldn't see many of the trends, negative trends in groundwater. But after data simulation, we could identify huge water storage depletion across the region in parts of Iran, in the Arabian country parts, and basically we face very challenging situation in the region in terms of total water storage and groundwater negative trends. Some more points about my current works, which I'm currently working on. First is basically data assimilation based on GRACE, but this time using ranging measurements. So previously, most of the works that I've been, or in general, GRACE data assimilation that has been done in literature are basically using monthly GRACE data. So my colleague and I are currently working on the idea of using GRACE level 1 data. So those monthly data are based on GRACE, processed GRACE data product into L2 and L3 products, rescale into monthly temporal scale. But now we have this idea of using daily measurements of GRACE data, the range measurement, and we try to use those products for assimilation. And the advantages are, the advantages of using GRACE L1B is basically that you don't need to do the data processing, converting from L1 to L2, which involves a lot of filtering and smoothing and losing some important signals. You can apply the data assimilation in the right location, right time. So accurately, you can apply the data assimilation whenever the data is available, and you can better detect sub-monthly signals. For example, if you have flash flood or something that I highlighted in this graph, you can better detect. So this is an imaginary, this is a exemplary a case study that my colleague and I have been working on. So the new data, which is in gray, has been compared to the conventional data from GRACE, which are highlighted in red and green, different solutions. You can see, for example, in this case, the gray was better capturing the high signal caused by flood in Eastern Australia. So there was a flash flood, sub-monthly, happened over just a few days. Usually, if you use monthly data, you miss that signal. And then you cannot improve the model properly. But using the new data, we can detect that, and we can better improve the model, which is, for example, can be seen in this graph. This is an preliminary study using the L1 data assimilation that we have been working on. You can see the blue graph better captures the rapid signal, which we usually miss when you use the conventional GRACE data.
Just another minute, Mehdi.
Yeah, sure. This is basically one of my last slides. So another data that I'm currently working on is the GNSS biostatic radar measurement. So we basically measure the signals, GPS signals reflected from land using the small sat CubeSats, and that data contains information about the land surface, atmosphere. In my case, I'm more interested in the land surface. So using that data, we can detect, for example, flooding. This is a case that happened in 2019 in northern Queensland flood. Again, very rapid signal, but we could see that Cygnus in this case, which is basically based on the reflected signal, properly detect the signals, properly detect the flood, as you can also see in this graph. And it can also be seen that the data is highly correlated to SMAP in representing the soil moisture variation. So that's another advantage. So with the current development in the small sats, and if we have a better constellation of satellites, you can imagine that how you can have access to this dense data, sub-daily resolution, and very accurate, and it's basically going to be very cheap, because what you need is just the GPS receiver or GNSS receiver. So in terms of study highlights, my study basically shows that using satellite emergency, there's especially with the new CubeSat topics, there is a great potential for improving land surface model and the calibration and the forecast. And but there are still room to work. There's still missing, for example, areas in operational, for example, land in hydrological data assimilation, specifically in Australia, which we try to cover with some collaboration that we are developing with Bureau of Meteorology and some other institutes. So I'm happy to discuss more if you have any questions after this. Thanks.
Very much, Mehdi, for the nice presentation. Any quick question to Mehdi? Just one before we move to the next presenter. Maybe just a quick one, Mehdi. How computationally expensive is it if you use daily GRACE product?
It depends on the scale. I mean, if you're working on, for example, 1 degree scale model, it won't be that that much of different from the conventional data assimilation that we do. But if you want to go higher resolution or bigger scale, for example, globally, yeah, it would be more. But the thing is, when we talk about daily GRACE data doesn't cover everywhere. So we're just focusing on the track. So that really doesn't add much to the computation, because we're only working on the tracks that we have data from on that specific day.
Okay, thank you very much, Mehdi. We reserve some more questions to you when we come to the general discussion.
Thank you.
Now, the next presenter is Dr. Kexiang Hu. Kexiang Hu has been working on groundwater, and he's a geology by background from bachelor's degree. He did his master's in GIS and then finally PhD in remote sensing of environment. Now, his main topic today is to look at the black box, that geological structure beneath the earth. So he's trying to come up with machine learning sort of technique to teach remote sensing data how to unearth what is behind that black box. So Frank, welcome, and welcome and present. Thank you.
Okay, thanks, Joseph. Just let me share my slides. Okay, is that working for everyone?
Yep.
Yeah. So, hello everyone. Glad to have this chance to present my very new topic, which is exploring hydrogeologic structure features at a large scale using groundwater machine learning models. So, from my title, I believe everyone knows that this is a course field topic which involves hydrogeology here, remote sensing, and computer science. Now, what I'm trying to do is very simple. The remote sensing, imagine there are three guys. The one guy from remote sensing will provide the data, whatever data we need. And the one from computer science will help us to do the calculation and do the model establishment. And finally, the hydrogeologist will analyze the results and tell us the story about the groundwater. That's what I'm initially, that's my initial thoughts. But later, when I try to dig something deeper, then I found there are really some gaps. There, like the most frequent question I was asked by some traditional hydrogeologists is that, how can you discuss groundwater without considering geology or said hydrogeologic structure features? So at that time, I could not answer this question because I know they are right. Now we can see so many remote sensing publications usually talks about the groundwater change and how it moves based on just grid signals or models without involving any hydrogeologic structure feature. This is somehow, how to say, ridiculous to hydrogeologists. I know this because my bachelor degree is geology, so I can understand why they say that. So that's why in the next I'm going to introduce some very basic concept of hydrogeologic structure features. So from my personal understandings, the definition of hydrogeologic structure feature is very simple. That is, anything affecting infiltration process can be called hydrogeologic structure features, like the terrain, soil, or even vegetation. But strictly speaking, in hydrogeologic field, the rock is the most relevant thing to hydrogeologic structure feature. You know, the traditional hydrogeologist intends to know that what kind of type of rocks in their study area, and are there any special geologic structure like faults, or like there are impermeable rock layers inside the aquifer or something like this, because this information will help us understand to understand the infiltration process, how it goes, and how groundwater flows inside the rocks, and how large the aquifer is, and as well as how much groundwater an aquifer can store. So these information are very important for environmental and water management. So that's why the traditional hydrogeologists think it's very important. They have to do this kind of field investigation for almost every area they studied. So how the field investigation goes, like for traditional hydrogeologists, so they will go to the exact place. If it's flat regions, so we drill some boreholes and fetch some rock samples and come back to laboratory, do some porosity test. So if it's in mountainous regions, we drill some caves or tunnels and directly go inside to see how the groundwater flows through the rocks and see if there are any special geologic structures, hydrogeologic structure like faults, because faults can somehow block the groundwater flows underground. So that's how we do it. And this actually is very useful to understand hydrogeologic structure features. But the problem is now we can't do this at a very large scale because it's very expensive, time consuming, and somehow dangerous. So also another problem is hydrogeologic structure features usually vary from one region to another. If you look at this picture, at a somehow like a large scale, it becomes very complex, too complex to analyze. So we really need some cheaper and safer solution to do to understand the hydrogeologic structure features in large scale. We need to find some new solution to replace the traditional hydrogeologic field investigation. So that makes now the new topic of mine. I'm not only considering the groundwater models, but I put a lot of focus on exploring the hydrogeologic structure features. So this is actually my the theory of my method. So we have a remote sensing still providing all kinds of data we need. We have a rainfall climate data, like a rainfall evaporation. We have terrain, surface terrain data, or vegetation and soil data, something like this. And we have groundwater data from Greece and some hydrogeological models. Then we use this data to train the machine learning models because the hydrogeologic structure feature is underground, we can see, so we can treat it as a black box, like we also know there are black boxes in machine learning, so we can combine this two together and figure a way to decode the black box, because we input some independent variables and we have some dependent variables. That's how we train the models, the machine learning models. Then the models will give some output parameters, and the final step is that the hydrogeologists will use their knowledge to tell us why the parameter say this, why the parameter say that, and how to explain this, how to link this to hydrogeology. So that's what we call decode here. So currently, we already have one initial study for Australia case. So we actually built a very simple binary models based on if groundwater recharged or not, and we used 5 independent variables as training data, so including rainfall, evaporation, soil moisture, surface runoff, and vegetation, and one dependent data that is groundwater. So here we create every pixel is an independent model for groundwater. So we can see some area we have reliable models which shows high accuracy, and in this region we can do the decode. But for some region with low accuracy models, so then currently we don't have any way to do the decoding, because even we do, the model is reliable, which means that the result of decoding is also unreliable. So for the decoding part, we try different ways of building models. We try different data source, training models, and see what's the influence. And we compare, we try to capture some parameters, like here we figure out the primary factor that controls groundwater recharge. So some are rainfall, some are soil moisture, and we map their spatial distributions. Also, because we do the binary models, we can get some information in what situation groundwater will charge, like rainfall over a certain threshold, and then we can do the decoding. So let me take an example to explain how we decode this information into hydrogeologic structure features. Like if one region is identified, the rainfall is the primary factor that controls groundwater recharge. So it means the rainfall and the groundwater has very direct links. So which means the rainfall recharge groundwater is a direct recharge mechanism. So to achieve this mechanism, the rock must have some very good permeability or have large porosity, so that rainfall can directly recharge the groundwater. That's how we decode. We use some kind of hydrogeologic knowledge and experience. That's basically what my topic. That's a story on what my topic. I know this is a very new topic because nobody has done before, and luckily our initial studies already proves that it's possible to infer hydrogeologic structure feature from using the remote sensing data, because to traditional hydrogeologists, it's this kind of concept they will not accept for now. But this study, the Australia case study, we already proved that it's possible. However, we still have so many problems in our initial study because currently we only consider limited parameters, 5 parameters that relate to the groundwater. But if you look at the water cycle map, you will find that there are still so many other parameters could affect the groundwater recharge. And then second, we do not consider the lag between groundwater and rainfall. And third, we do not consider the groundwater flow, the horizontal flow inside the rocks. And we do not test all machine learning methods. Some machine learning methods like deep learning, they may show more advantages for building the models, but we haven't tested. Also, for our results, because we only use the model data, we did not use the real observation data, so we still lack of validation. And finally, the hydrogeologists have a very different concept about the scale for like 100 kilometers squares, 10 to 100 meters square. For hydrogeology, it's very, very large beyond their imagination. But for remote sensing guys, 100 kilometers square is not large. So that's a gap between these two fields, and that's the future direction and the problems we need to address. Okay, and I think that's all. So yeah, thank you.
Thank you very much, Frank. Any question, quick one from participants to Frank? Maybe just a quick one, Frank.
Yeah.
How deep is your black box?
Sorry, what?
How deep is your black box?
It depends. It depends on the various region. If the recharge mechanism is very complex, for example, not only rainfall controls the groundwater recharge, but also others, like, let me show you this figure. This green area actually it shows the vegetation controls groundwater recharge. So it relates to the biologic field. And I cannot explain the real recharge mechanism controlled by vegetation. But when we see these green regions, it shows wetlands. It's all wetlands from national parks. So it depends. The black box could be very simple, or it can be very complex. It depends how many factors or what aspects, what the factors controls groundwater recharge. Yeah, that's my answer. Thank you.
Thank you very much, Frank. We'll have more questions for you during the discussion time. So to introduce our third presenter, Adam MacLeod. Adam is the program manager at AquaWatch, to just tell us the state of the art of Aqua. Thank you. Welcome, Adam.
Thanks, Joseph. Can everyone hear me okay?
Yes.
All right, I'm going to share my screen if I can. All right, is that coming through?
That's good. Thanks, Adam.
Terrific. Okay, so first of all, I just want to say thanks to Earth Observations Australia for hosting this webinar and asking me to talk today. I'm actually sitting in on behalf of the AquaWatch mission lead, Alex Held, who's traveling at the moment and has asked me to present on his behalf. I also want to start by acknowledging traditional owners of the lands where we work and live. On behalf of myself and the CSIRO, I live in Adelaide, which is the traditional home of the Kaurna people, and they're traditional owners of this land. Today I'm going to talk a little bit about the AquaWatch mission, which some of you might be familiar with and some of you might have even heard about in this forum before. But I believe it's been a little while since we've had an update, so I'm going to give a brief update of where we are and recent news. So AquaWatch is a CSIRO mission that's being done in collaboration with the SmartSat CRC. CSIRO has established these range of missions, which are essentially programs, but they are established to address a grand challenge. And they're typically characterized by partnerships of public, private, and research organizations. AquaWatch is one of about a dozen missions. Others are covering things like renewable energy, future protein, and food resilience, and also drought resilience. But on AquaWatch, the goal is about supporting healthy and sustainable water systems and resources. When we talk about water systems and water resources in AquaWatch as well, we're talking about inland water, so lakes and reservoirs, rivers and streams, as well as estuaries and coastal waters, and helping to address some of the emerging and current issues related to water quality and supporting better quality water for society, the environment, and for industry. Most of the work that we're doing on AquaWatch is aimed at supporting water systems within Australia, but we hope that eventually AquaWatch will also have a global footprint. And you can see down the bottom of this slide, we've identified 3 of the United Nations Sustainable Development Goals there as well, which AquaWatch overlaps pretty heavily with. So SDG number 6, clean water and sanitation, SDG number 14, life below water, and 17, which is partnerships for the goals. And the SDGs themselves, in a sense, represent missions, although that's kind of, it becomes a little bit academic at that point. But AquaWatch is a mission which is really about providing information, supporting monitoring, modelling and forecasting, and management of water bodies around Australia and the world. AquaWatch is also a system. So the goal of the mission is to support those objectives of water quality, but we're doing it this way. The system which we're aiming to design and develop includes 3 major subsystems. So we envisage that AquaWatch will include a constellation of Earth observation satellites. Initially, those satellites will be the existing satellites, which we have data streams from, including Landsat and Sentinel and MODIS, as well as the emerging constellations of hyperspectral imaging spectrometers that we will have access to data streams from. Long term, we hope to have bespoke, custom-built AquaWatch satellites included as part of the system as well. And to that end, AquaWatch has been named in the ASA's Earth Observations Roadmap. Complementing the Earth observation satellites, we'll have a dispersed network of in situ sensors. And these sensors might contribute any data, water quality parameters that aren't detectable from space. So they might detect salinity, pH, dissolved oxygen. It might be weather stations. In some cases, we'll also be using imaging spectrometers in those in situ sensor deployments. either to provide information about the light reflected from water and what we can directly infer about the chemistry, or as a source of data for calibrating the satellites against. So between the Earth observation satellites we'll be integrating and ingesting data from, and the data from the dispersed network of in situ sensors, all of those things will be ingested to our data integration system, which will be a cloud-based system for essentially establishing a high performance processing pipeline. Data archive will be stored in the cloud, and all the processing using scaled computing also in the cloud. And essentially what we have then is a big funnel, a multi-sensor system ingesting as much data as it can from as many different sources as it can. Data being reduced and pre-processed, parsed and formatted in the pipeline early stages, then modeling and forecasting, including that using artificial intelligence, and presentation layer for end users through the data integration system. So we describe AquaWatch as a weather service for water quality. We're essentially monitoring the water, including content and chemistry, supporting the modeling and forecasting based on rich or augmented data sets, including process-based models and data-based models. So when I say process-based models, that's a more traditional type of science approach. Data-based models implying artificial intelligence and machine learning. And eventually, once we have enough training data, supporting that forecasting on any time scale. And through that provision of data and the high-level data products, supporting management of water bodies, interfaces, alert systems, apps, etc. And like a weather service, with AquaWatch, we aim to provide high availability, broad-based modeling and monitoring, reliability, provenance of data, and quality control over the data to support those higher level goals of monitoring, forecasting, and management, providing a range of data products to end users across Australia and the world. The AquaWatch mission scope. So AquaWatch is a system that will take more than a decade to complete. And even at that point, once we say it's complete, once it's finished as a project and we've met the requirements and specifications of that project, it can continue to operate and evolve and grow over time with new sensors being ingested and with functional enhancements being implemented. That's a long way down the track. What we're looking at really over the next few years is the development of AquaWatch to an operational system, an initial operational system by the end of 2026. And we've given it the name AquaWatch 2026. In that time frame, we hope to establish around 15 to 20 operational sites with in situ sensor deployments. We're targeting a cross-section of Australian states and territories, a cross-section of end user groups and user applications. And within the 15 to 20 as well, there'll be some stations which are dedicated to calibration of Earth observations imagery from satellites. And there'll be some pilot sites which are also located overseas. As we go, we're proving the system, we're validating it and evaluating it. And we're also establishing a community of practice around the kinds of data products that we can derive. And some of that community of practice will be doing early science based on the data products that we're creating over those few years. But essentially by 2026, we're aiming to have what we call an operational system with that end-to-end vertical integration, including that broad-based, well, that initially relatively broad-based sensor network, data streams from existing satellites, and science processing pipeline for what we call core functionality, tested for performance and validated against impact. then continuing to grow and evolve from that to the end of the mission between 2030 and 2035, by which time hopefully have bespoke satellites. And beyond that, it becomes more of an ongoing operational consideration. AquaWatch mission within CSIRO got the official launch in March this year. That was very ably and deftly handled by our new communications manager, Megan Thompson, who's featured in the top right photo there. But also in these photos, you can see Ed Husick, the Science Minister, Tanya Plibersek, the Environment Minister, Larry Marshall, former CSIRO chief, Alex Held, who is the mission lead, who I'm standing in for today, as well as representatives from the SmartSat CRC, who are our foundational partner in AquaWatch. You'll see in a minute that the range of partnerships and the team size that we've grown to extends beyond just CSIRO and SmartSat CRC.
One more minute, Adam.
Sure thing, thank you. About the same time, we were presenting at United Nations, and again represented here by Alex. This slide is partially about United Nations, but also you can see the First Nations water issues being highlighted there. And Indigenous engagement in AquaWatch is something that we're quite attentive to. So through consultation, through co-design and co-development, we're aiming to get First Nations representation in AquaWatch at all levels. Okay, accelerating a little bit now. Here we see the development progress. So while we went through that process and that ceremony of getting AquaWatch launched within CSIRO, which created the media coverage and essentially gives us that certainty and commitment from the CSIRO executive until the end of 2026, the work has already started in development of the system. Two things are happening here. We're essentially designing AquaWatch in a typical top-down waterfall approach, so developing overall scope, budget, schedule, doing communications, developing system requirements based on the end user requirements. But at the same time as we're doing that, we're also starting to build AquaWatch from the ground up through pilot projects. And each pilot project seeks to establish a new site for sensor deployments, integration of sensor data with satellite data under our data processing pipeline, and to demonstrate and prove AquaWatch in that application. And as we do that, the pilot site and the processing modules that are developed under that pilot project are integrated under the overall AquaWatch system. All right, last couple of slides here. Sorry, Larissa, one up very quickly, but this is a slightly technical functional block diagram that I did for AquaWatch, belies my experience as a system engineer. The reason I show this is because it illustrates quite a nice functional decomposition of AquaWatch. The Earth observation system and the in-situ sensor system, you can immediately see that the blocks within those can be scaled as new sensors are added, with attention to interfaces there. Meanwhile, the data integration and analytics system, the processing pipeline, quite complex, but something that can be developed using agile or scaled agile approaches, develop a core set of functionality and supporting its evolution and functional enhancements over the life of the mission. I had a couple more slides, Larissa, but that's it. That's probably a nice place to stop.
Okay, thank you very much, Adam. And now we can open the forum for discussion. So if you have any question, feel free to write through chat or just raise your hand up, and then we move on from there. So any question from participants?
Maddie.
Hello, everyone. It's Mehdi here from University of Southern Queensland. I have a couple of questions for Mehdi, if that's okay.
Yep, that's okay.
Mehdi, great talk. I enjoyed. First question is, you mentioned GNSS reflectometry, and I was wondering if you're talking about a private satellite, like CubeSat private satellite, or you're talking about Cygnus.
Yeah, I haven't enough time to talk about this. Thanks for raising this. So there are two. One from private company like Aspire Global, which you can apply for data through ESA, for example, to get some maybe sample limited data. But if you need more, you need to basically use to purchase the data. But for that specific study, I've been using Cygnus. Cygnus is freely available, and it's and that was the data that I used for those graphs as well.
Is there any CubeSat over Australia doing this, like a private company, or?
They're working on the topic, and I think there's been a few launch of CubeSat, but there is no data at least available at this point. But I know that the people are working. So, yeah.
For that purpose? Oh, okay, cool.
Yeah,
okay,
yeah.
Cool. And next question is, would you please explain how do you deal with the uncertainty for assimilation, since you're dealing with a lot of the different types of data set? I'm asking this.
Yeah, so it depends on the data. So for example, if you are working on satellite soil moisture, depend on the platform, you can get some uncertainty from the data providers or based on literature. People are doing the data assessment globally, so we can get some understanding about the uncertainty of the observations in different areas. In terms of GRACE, we can do some estimation in GRACE. There are basically two different approaches. Once people are using just basically specific error value based on arbitrary trial and error, I would say. You can also get some estimation based on spherical harmonics for monthly measurement. For level 1 data that we are currently using, there is not much information around. So in our preliminary test, we just assume that 10% of the data are associated with the uncertainty.
What's the product of B1, like LB1? Which product? Is it JPL, CSR? Which one is it?
That one, I think it's CSR. My colleague was working.
It's coming from Shinchan. If it is Shinchan, it's CSR. Yeah. Okay, cool.
Yeah.
Cool. Thank you, Mehdi.
Shinchan and Khosrow. Yeah, they've been both working and collaborating on this. Thanks.
Any question? Maybe just to follow up on that. Most of your examples were based on Iran, South America, and the Middle East, with Australia coming towards the end, where you just had the daily GRACE data.
Yeah.
Is there any attempt you have made to assimilate data into the Australian water resource model, Aura model, and see if it can improve or something like that?
We've done that using the monthly data. This actually my first effort was using the GRACE data for improving water storage over Australia. I didn't show the result, but the main reason I stressed on those other regions was the fact that there are much not data in Australia. We have a good data sets available, but still, if you want to use a model for some sort of long-term monitoring and uniform monitoring across the continental, the models are very useful, and using data assimilation, we can improve those models. We used monthly GRACE data, we use multi-mission satellite measurements for data assimilation, and we currently are using the new data over Australia as well.
Thank you very much. Adam, there's a question on chat you may want to respond to on the link of AquaWatch Australia to AquaWatch program in the international group.
I'm sorry, Joseph, I didn't get that. Was that directed
There's a question from Megan on chat.
Yes.
She's asking, what links does AquaWatch Australia have with AquaWatch program in the international group of Earth observation?
Yeah, we do have some connections with them. They're more at the discussion level between Alex Held, the mission lead, and Flora, who's our international liaison manager, and Geo. I've not been that involved with that discussions. I know that we have a fairly open, transparent relationship with them. I believe that they are working on something along the same lines, but the activities that are happening under the AquaWatch mission at the moment are happening in parallel. They're independent of GEO. We don't have a formalized partnership or relationship with them yet.
Thanks, Adam. And just while you're still there, I would like to ask, is there any reason why you're just focusing on the water quality and not water quantity?
Yeah, so the reason is essentially that there are already lots of systems that are there to monitor water quantity. There is an expectation that AquaWatch will implicitly be able to detect water quantity. What we're seeing is light reflected off the water. So we can see the extent of the water body, but in terms of measuring below the surface, that's something that we're not really aiming to do. There may be some instances where we deploy a system, and just because of the nature of the work or the application that we're trying to address, it may involve some flow sensors, but generally we're looking at using satellites to monitor the reflectance from the water body surface, and then combining that with data from in situ sensors.
Thank you very much. Any other questions for our presenters? Maybe for Frank, just I thought I was thinking while you are presenting, is there a chance that you could use Mehdi's assimilated product, which will give you more better grace input to your modeling or your black box to improve anything?
Sorry, I forget to unlock the mute. Yeah, it's possible. Actually, because machine learning purely belongs to the computer science field, and why it's popular, because it does not require any knowledge about the hydrogeology or remote sensing, as long as we have the data, so we can input and train the models. So we don't really, the computer science guy really don't have to understand the remote sensing, the groundwater, the climate, or the hydrogeology sort of things. Then they still can create the models. But one thing for machine learning model is they require quality data. So if the data you train have a lot of noise, or it's inaccurate, or if you want to train a groundwater model but you didn't use relevant parameters for groundwater, so then it becomes meaningless. So that's why we really need Mehdi's skills, because he understand remote sensing. He understand what in what regions what data is best for creating groundwater models. Yeah, so I think that's my answer. Yeah.
And just while you're still here, Frank, any chance to use reanalysis data rather than GRACE data?
Not sure. Not sure currently, because we have to do the validation, because the Mehdi's model have a lot of uncertainties. Like even for rainfall models, the very high spatial resolution. I tried one very high spatial resolution rainfall models in mountainous region, and I found it did not match at all. So it depends. If in flat regions the reanalyzed model, the data is accurate, then we can use. But if it's not, then depends on the accuracy of a model. For now, GRACE offers the real observation data, then we can rely on it. But the model is just simulation. If no evidence proves it's accurate, then we cannot use this data, or it will generate a very bad model, or even generate a misleading models for groundwater. Yeah.
Okay, thank you very much. Let me take this time now to thank our presenters, Mehdi, Frank, and Adam, for the nice presentations, and also for the participants for getting time to attend. We'd like to thank you very much and wish you all the best. Hopefully you have gained some knowledge about water situation in Australia. Thanks also for Earth Observation Australia for making it possible for us to have such a webinar. Thank you, Megan, and thank you, Larissa, for putting together all this. Thank you very much. Bye-bye.
Thank you.
Thank you, everyone.
Thanks, Joseph. See you, everyone.
Bye-bye.